On June 5, 1976, workers at a newly built dam in Idaho noticed two small leaks trickling from its base. Nothing alarming at first, the kind of seepage engineers see fairly often. Within 6 hours, those leaks had grown into a breach that emptied an entire reservoir and sent a wall of water through the valley below. The dam had never even finished filling for the first time. The Teton Dam was built by the U.S. Bureau of Reclamation on the Teton River in southeastern Idaho, authorized by Congress in 1964 and finally constructed starting in 1972. At 305 feet tall, it was designed as an earth-fill dam built from compacted soil and rock rather than concrete, intended to support irrigation, flood control, and power generation for the surrounding farmland. Earth-fill dams like this one rely on a very different engineering approach than a concrete structure. Instead of one solid, rigid barrier, they're built in compacted layers around a dense, impermeable core designed to hold back water through sheer mass and careful material selection rather than structural rigidity. The site itself, though, sat on geology that would prove to be the central problem. Volcanic rock riddled with natural cracks and fissures in a region with a history of seismic activity. Making a dam's foundation watertight on ground like this is a serious engineering challenge, and it's the challenge this project didn't fully solve. To seal a foundation this fractured, engineers cut what's called a key trench, a deep slot cut into the bedrock beneath the dam, then filled with fine, densely compacted soil to block water from seeping through the rock underneath. The Bureau of Reclamation also pumped grout, a cement-based sealant, into the surrounding rock fissures to further reduce leakage. The soil chosen for the key trench and core was a wind-blown material called loess, fine-grained and effective for creating a watertight seal under normal conditions. But loess has a specific vulnerability. It can crack easily under certain stresses, and once water finds a crack, loess erodes quickly, particle by particle, in a process engineers call piping. The investigation that followed identified two compounding weaknesses in the design. First, the shape of the key trench itself created conditions where the fill material could crack under pressure, particularly where it met the fractured rock walls. Second, given how fissured the volcanic bedrock was, sealing it completely with grout alone was, in practical terms, extremely difficult to guarantee. Investigators later concluded the design simply hadn't adequately accounted for how challenging this specific foundation would be to seal. Adding to the risk, construction delays had pushed the schedule back, but the decision was made to begin filling the reservoir anyway, before the dam's low-level outlet works, the mechanism that would have allowed engineers to quickly drain the reservoir in an emergency, was finished. The reservoir began its first fill in late 1975. By early June 1976, filling was proceeding faster than originally planned. On the morning of June 5th, workers noticed two small, clear seepage points near the base of the dam's downstream side, an amount of water small enough that it wasn't immediately treated as a major concern. Within a few hours, though, the seepage had visibly grown, and by late morning a whirlpool had formed on the reservoir side of the dam, a sign that water was actively being pulled into a growing channel inside the structure itself. Bulldozer operators attempted to fill the growing hole, but the erosion was already moving faster than it could be countered. Evacuation orders went out to downstream communities as the situation escalated. At 11:57 a.m., the dam breached completely.
Cameras that happened to be filming captured the moment the whole structure gave way, sending an estimated 80 billion gallons of water surging down the valley. 11 people died, according to the most detailed case study analysis of the disaster, though some broader historical counts place the toll as high as 14. Thousands were left homeless, and damage estimates reached into the hundreds of millions of 1976 dollars.
The independent panel convened to investigate the failure. 10 engineers and scientists with no government affiliation, appointed jointly by the Secretary of the Interior and the Governor of Idaho just 2 days after the collapse, concluded the dam failed through internal erosion or piping in the key trench deep in the dam's right foundation. Their finding was less about a single mistake and more about a failure of anticipation. The report's central conclusion was that the design simply hadn't adequately accounted for the specific, difficult conditions of this foundation, fractured volcanic rock that made a fully watertight seal extraordinarily hard to achieve with the methods used. Investigators also noted a lack of clear communication between the engineers who designed the foundation treatment and those who carried out construction, which may have compounded existing weaknesses. Unlike several disasters in this series, this wasn't a case of a warning being dismissed for cost reasons. It's a harder, more uncomfortable kind of failure. Engineers doing careful, good-faith work on a genuinely difficult site and still not fully grasping the risk until the ground itself proved them wrong. The Teton Dam was never rebuilt. Congress ultimately declined to fund reconstruction, and the site today serves largely as a visitor overlook and a case study for engineering students. The failure led to significant changes in how the Bureau of Reclamation and similar agencies evaluate dam foundations, particularly fractured rock sites, and pushed broader adoption of more conservative safety margins in earth-filled dam design nationwide. It remains one of the most closely studied dam failures in American engineering history, not because anyone was negligent in the way some other cases in this series describe, but because it demonstrated just how much can still go wrong when a foundation's true behavior isn't fully understood until the water is already flowing through it.